My name is Tanay Malla, and today I'll be presenting the infrared spectroscopy of HCl and DCl. The aim of this experiment is to utilize IR spectroscopy to create rotationally resolved spectra of the vibrational motions of HCl and DCl. We hypothesized that since HCl has a lower reduced mass than DCl, the transition will be indicated at a lower frequency. Additionally, HCl will have higher resolution peaks than DCl due to the greater mass of deuterium narrowing the spaces between rotational energy levels. For some background in theory, vibrational and rotational energetics are highly intertwined, and as such cannot be studied individually. The primary and fundamental energy transitions occur from the V equals 0 and goes to the V equals 1 levels. Individually, this energy transition releases infrared radiation at a wave number of approximately 2100. According to the ideal harmonic oscillator, this should be the only possible transition. Due to anharmonicity, though, we were also able to observe an overtone frequency in which a transition occurs from V equals 0 to V equals 2. Rotational transitions, as opposed to vibrational, are much weaker, only resulting in transitions of approximately 20 wave numbers. These rotational transitions only change by plus or minus 1. Because of the small transition, we need to have very highly accurate IR readings to be able to witness these peaks. When transitions are paired and the rotational energy level increases, this group of transition is referred to the R branch, which is indicated by the black lines on this diagram. When the vibrational level increases and the rotational energy is unchanged, it would be referred to as the Q branch, but this type of transition is forbidden. Finally, when the vibrational energy increases while the rotational energy level decreases, this group of transitions is referred to as the P branch, as indicated by the blue lines. When analyzing vibrational and rotational energetics, there are several molecular constants and physical parameters that can be measured. First, Be is a constant indicated by this equation in the top right. To account for vibrational excitation, Be can be altered further. A component of the equation for B is alpha E, which represents the rotational and vibrational coupling constant. Alpha E can be determined by this equation. Finally, D represents the centrifugal distortion constant. This constant is several magnitudes less than B, and as such is only significant at highly rotationally excited states. As a part of the sample preparation, D2SO4 and potassium chloride were reacted to create deuterochloride gas as well as potassium sulfate. This reaction was similar for HCl, whereas H2SO4 was used instead of D2SO4, producing hydrochloric gas instead of deuterochloride. This reaction is exothermic and produces gas, so the setup had to be provided carefully to prevent any gas leak, as hydrogen chloride gas is very toxic. Unfortunately, during the sample preparation, the sulfuric acid was injected too quickly, resulting in the solution bubbling out into the rubber tubing. It is unclear whether this had an effect on the data, because prior to this incident, the D2SO4 stock was barely adequate for our experiment in the first place. We believe that the solution may have been saturated with hydrogen since it had been used until its last drops. When our sample was analyzed using the IR spectrometer, the DCl overtone peak was indistinguishable from the background, and the DCl fundamental peak was only slightly visible. For this reason, we needed to use sample data provided by the lab instructor to proceed with our data analysis. The IR spectrometer used for this experiment was the Perkin-Elmer Spectrum 2, which is a Fourier transform IR spectrometer. The instrument used the following parameters in this table below. After analyzing our original samples using these parameters, we decided with the lab instructor that our data was unusable and that the suitable data would be provided for us. As a part of data analysis, we gathered the total IR spectrum that was provided by the lab instructor. To start the analysis, we will go from left to right, starting with the most energetic, the DCl, first overtone. In the top left graph, we can see a zoomed-in image of the total IR spectrum to show the distinct rotational peaks. For the R branch on the left, there were 8 distinct peaks, while the P branch only had 7. The wavelength of each peak was assigned an energy level and plotted on the bottom once more against its energy level. A tertiary polynomial function was used for regression analysis, and these lines of best fit resulted in the equations that could be related to these equations that indicate the P and R branches. By comparing these two equations, we are able to determine several constants that are displayed in the table below. Continuing down the graph, we come upon the first overtone of HCl. On this graph, the same regression analysis is completed. The R branch had 12 distinct peaks, while the P branch had 11 distinct peaks. Since the DCl first overtone was less distinct, the second smaller peaks were not visible. These smaller peaks indicate possible phosphorus isotope or chlorine isotopes that were present in the sample. Additionally, a regression analysis was completed to find the following constants. The third peaks present on the graph belong to the DCl fundamental transition. Here the peaks are very distinct, and the R branch had 11 peaks, while the P branch had 10 peaks. The analysis of the fundamental transition is slightly different from those of the overtones, and these different equations are indicated in the top right. Again, the regression line was compared to these equations to determine the constants. Finally, we have the HCl fundamental transition. Relative to the DCl fundamental transition, the HCl peaks are noticeably narrower. This supports our previous hypothesis that the HCl peaks would be more distinctive. Additionally, there are more rotational transitions, whereas the P and R branches both had 17 peaks. After collecting all of the data, the calculated values for the constants were averaged, and an interval was calculated using a 95% confidence. As we can see, the alpha E values and BE values were statistically significant, but the D values did not have enough accuracy. The VE and XE times VE values were calculated using the following system of equations. We can see that alpha and B values were both significantly different in the two hydrogen isotopes. Furthermore, displayed are the reduced mass values. Using these values for the atomic mass of each element, the force constant was calculated using a modified version of the harmonic oscillator equation. The bond length was also calculated using this altered rotational constant equation. Unlike the alpha and B values, the force constant and bond length were unaffected by the hydrogen isotope present in each molecule. In conclusion, we are able to effectively utilize IR spectroscopy to analyze the effect of different isotopes on rotational and vibrational transitions. We ultimately found that the isotope has significant effects on the vibrational and rotational coupling, but does not affect the bond elasticity or length. Ultimately, IR is a very useful spectrometer and can be used in a variety of different analyses. Thank you.